Welcome to another Directions Mag Geospatial webinar, today sponsored by Hexagon Geospatial. I'm Barbary Duke, Managing Editor here at Directions Magazine, joined by my assistant webinar producer, Lynette Qualia. If you have any questions about your connection, just drop us a note in the chat. We'll do our best to help you. We encourage you to read our feature articles, as well as news, and view more geospatial webinars at directionsmag.com. We are standing by to take your questions. Type those into the question box at any time during the webinar. We have so much to cover in our 30 minutes today that we're collecting your questions, and the team at Hexagon will follow up with you personally. We are recording today's webinar, so keep an eye on your inbox in the coming days for that link. And we appreciate your opinions on the surveys and things that come along. We have the opportunity to speak today with Robert Gammon. Excited to have him. He is going to give us many examples and all the details on how you can incorporate smart monitoring into your workflows for your organization. Robert, we're excited to have you with us today and to learn more about this. Welcome.
Perfect, and thank you very much for that introduction. So I'm going to start this with welcome, 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 and thank you for taking the time to join us today. Today we're going to explore creating smart monitoring applications with real-time data, machine learning, and 2D, 3D dashboards. We have a ton to cover, so let's actually go ahead and just get started. We have 4 themes we're going to explore today. Data sources, and these are referred to as connectors, geospatial processing, including the integration of machine learning, dashboards, a collection of tools for 2D and 3D visualization and analysis, and deployment for desktop, mobile, and web applications. We will discuss these themes in context of 4 applications, namely a flood damage and economic impact application, crash analysis using digital reality application, plume modeling, response planning application, and automated agriculture mapping and analysis application. The paradigm we use for all 4 of these applications is the same, and everything starts with data. We have your traditional GIS data, we have satellite data, we have IoT devices, we have airborne data, we have unstructured data, and we also have meteorological data sources. This data can be transformed using a spatial model. Spatial modeling includes a rich collection of raster operators, vector operators, image processing operators, and machine learning approaches. These applications can be easily created using configuration. More specifically, little to no programming skills are required to create your application. However, if need be, M.App Enterprise includes a robust API, and this API can be used to create highly customized applications. Next, the user can deploy applications within a couple of clicks. As noticed in the previous slide, applications can be designed for desktop machines, mobile devices, and web browsers. Finally, the collection of applications that have been created for specific smart monitoring initiatives can be used to solve specific geospatial challenges. Remember, smart monitoring initiatives can include a collection of applications, be it desktop, mobile, or web-based. A geospatial initiative can be made up of a combination of applications, and these applications can be used to promote collaboration. Specifically, these applications can be used in tandem to monitor, evaluate, and act. All of these applications share data, and this allows the user to easily communicate with one another. And this allows them to make the decision-making process to be cooperative. Hence, there's a built-in feedback loop. Namely, the applications can be used to monitor, evaluate, and then act, evaluate, and monitor. The enterprise approach is key, as there are a number of variables that need to be managed when tackling a geospatial initiative. First off, we have administration. Administration sets the stage for who can access what, be it access to the applications themselves or access to the data within the applications, including the read, write, or editing rights capabilities. Application creators, not software developers, can build, deploy, and maintain these applications. And this is really key that I want to go over, is it's not about software development, it's about being able to configure these applications and be able to deploy these applications. As with most projects, multiple initiatives tend to run in parallel, and hence there needs to be able to manage these in a logical collective fashion. So here we have Initiative A, and Initiative A can actually be made up of multiple applications. And those applications can then be used to monitor, evaluate, and act. But of course, you can create multiple initiatives and you can have those running simultaneously. And of course, your users can cross these boundaries without any problems whatsoever. This is truly an enterprise approach for managing all of your geospatial projects. Like with the previous slide, various actors can actually share data and can act collectively as a team. This allows the decision-making process to be a collaborative one. So let's get started. Let's actually jump into this and take a look. We've actually set up 4 applications for you today. Our first application is flood damage and economic impact. This application uses readily available imagery to automatically delineate areas of flooding and then uses the results to understand the economic impact. Once an application such as this is configured, it can be reused again and again, as the geoprocessing is set up to handle the transformation process and in turn automatically feed data into the dashboarding application. This example relies heavily on geoprocessing and the 2D/3D visualization components of M.App Enterprise. So a typical hurricane contains a ton of energy, and this can cause extreme local flooding conditions. In the case of Hurricane Harvey in August of 2017, local areas experienced winds in excess of 130 miles per hour and approximately 40 inches of rain. These conditions affected 30,000 people, of which 17,000 of those folks had to be rescued. The entire event caused approximately $125 billion of damage. So with that in mind, what we wanted to do today is give you a live demonstration on what we built to tackle that. So what you see here is kind of a blank screen, if you will. We just have an aerial photograph, and that aerial photograph is showing us where the water is before the event. If we go into the upper right-hand corner over here and we take a look at layers, you'll notice we have a number of layers that are created. And these were actually created using the geospatial process. If I simply take the post-flood image and I move it up one, you'll notice that you can see there's quite a bit of flooding in this particular area of Houston. That's quite useful in itself, but it'd be nice to be able to take a look at the before and the after simply by dragging across the image. So as I'm dragging across the image, you can see the areas that got flooded. Well, with the geoprocessing that we have set up, we can actually extract information from those data sources. Most notably, we can find out where the water was before the flood happened and occurred, and we can also use the post-flood image to pull out where the data or where the flood was after the event. So in this particular case, that's quite useful. We have 2 pieces of information that we can then use to create our third piece of information. And our third piece of information in this particular case is, where did the water go? Where is it actually flooding? All of what was shown only really paints a picture. More specifically, there's no actionable information at this point. The geospatial spatial model used to drive this application takes this raster information and attaches meaningful attributes to the parcel fabric. With this information in place, we can now use the widgets to get a better understanding of the economic impact and flooding within this area. So what I'm going to do now is I'm just going to basically go ahead and turn everything off and go back to a blank screen. And most notably, we have the parcels. And as I mentioned before, those parcels themselves now have attributes about the flooding conditions. They've been painted from a sort of light green into a dark red, but we don't really have a legend at this point. So let's go and turn a legend on. Now, this isn't your traditional legend per se. It's actually a widget which has a pie chart in it. And that pie chart now represents the thematic representation of the polygons. We can use this to quickly cross-filter. I can say, show me everything 90, 80, 70, and 60, and 50, and you'll notice how fast it is. And the key component is once this has been set up, once the geoprocess is run, you can run it from area to area to area to area, completely reusable in this particular case. So what I want to show now is the ability to take a look at cross-filtering. So I'm going to turn on some additional widgets here. And these additional widgets let us take a look at the damage designation, for example. So if I wanted to do a cross tabulation of where all the residential 1 areas are, well, and let's say from 60 to 100% coverage, you'll notice that that represents $25.46 million in damage. So this is an effective way to be able to quantify not only where the damage is, but how much damage has occurred. What we also wanted to do for you is we wanted to bring in a 3D aspect. And the 3D aspect here is basically a representation or a representation of that 3D thematic map. So I'm just going to reset this so you can get a concept of what this is and what's going on. So as I move in here, you'll see that each and every parcel is now basically being extruded, and it's being extruded by the percent coverage. So all of the filtering that we saw before still works exactly the same way as it did before, but it's now representing that data in a 3D environment instead of just a traditional 2D environment. And what's one of the key components that we've added to M.App Enterprise is this 3D component that we have. So that's very nice to start with. That's our application number 1. So let's move back to our presentation. And let's go to application number 2. And this is using crash analysis using digital reality. This application integrates crash location data with street level LiDAR data. The application you're about to see is used to easily identify dangerous intersections and road segments based upon crashes. However, the power of this application lies in the digital reality integration approach that we used. Namely, the ability to use street-level LiDAR to examine crash scene and to determine if safety measures should be implemented. This example relies heavily on our LiDAR data connector, our 3D visualization, and on our 3D measurement components within M.App Enterprise. As many of us have likely heard, flying is a lot safer than flying is a lot safer than driving. For every 5 million driving accidents, there are only 20 related flying accidents. To provide some context, in Tennessee alone, there were approximately 200,000 accident reports, 48,000 injuries, and 1,000 fatalities in 2018. This all occurred on about 14,150 miles of state roads. So that's just one state. So you get a real good idea of how much of a problem this can be. So with that in mind, let's go to the application. In this case, it's a video. I would have liked to have shown it live. I just didn't have time to put it all together. So I'm going to go and do a video here. But let's set the stage. So we have our widgets like we had before. We have the collision type. We have the posted speed limit. We have the accident type. We have this date, so that allows us to look at change over time, and what we call a heat map. And basically what this does is it shows you sort of what's happening on a day-to-day basis and from what time it's actually occurring. So you'll see that, you know, during the high peak traffic areas, that is a little darker in that particular case. So let's start this up. So we can do the hotspot, traditional hotspot mapping and turn that on. And that gives you a concentration level of where these incidents are occurring. You can, of course, look at change over time. Many of you have probably seen this before, but it's wanted to show you the dynamic nature of being able to cross-filter. Now what I want to do is drill down and look at a heads-on collision with between 30 and sort of 45 miles per hour. And it isolates one that fit that criteria. And that one that fit that criteria is actually at an intersection in this particular case. Oops, sorry. I hit the wrong button. And that's one of the problems with videos is if you miss it, you kind of got to go back and redo it a little bit. So again, we're just going to go and we're going to do the heads-on collision, and we're going to set it between sort of 30 and 45 miles per hour. Once you have that, we can click on that to get some further information. Here we're going to click on it, we get some details, but here's the key, the digital reality component that jumps in. So each and every one of these intersections can have information about the layout of this intersection. So we can actually go ahead and we can zoom in. Now this is all being done over the web. So we're serving massive amounts of LiDAR data over the web, and we have the ability to change its point size so that we can get a really good representation of what happened at that particular site. And in this particular case, it was a head-on collision between a motorcycle and a vehicle itself. So what we can do is we can use the tools available to us to quickly gain a better understanding of this. So we can do some measurements to get an understanding of what the distance was between those. We can also use this to take a look at where signal posts were, these kinds of things. It gives you a good lay of the land. But what we wanted to do here is we wanted to see what was going on with the vegetation. So we just bumped the points up a little bit, turn on the orthogonal measuring component, and basically do a measurement. And you'll notice that in that particular case, that particular piece of vegetation was 4.16 meters above the street itself. As you can see, the ground-based point cloud can provide an accurate model of intersections, and this can assist in understanding the crash scenario. Safety engineers can use this information to help with the understanding of vegetation, signage, and signaling position. Once you're done, you can simply just click on the C, go back to where you were, and start over again. The beautiful component here is that all that LiDAR data is being served up via the web and is accessible through a simple web application as you're seeing here today. Perfect. Let's go ahead and take a look at our second example, or sorry, our third example. Plume modeling, response, and planning. This application integrates machine learning, predictive modeling software, and real-time sensors all within a single application. In this particular case, the predictive modeling software that was used was developed by Lakes Environmental. Lakes Environmental is recognized internationally for its advanced air dispersion and modeling software. Their applications can be used to model a wide array of particulates and can use global meteorological data to predict how pollutants move through the atmosphere. This particular application relies heavily on the robust API. So that API is key here because it allows us to create a highly customized application. And it also relies on the 3D components of M.App Enterprise. So to provide some perspective on airborne pollutants, a human breathes about 3,400 gallons of air each day, which is about 2 gallons a minute. Ambient air pollutants from sources such as power plants and industries were responsible for 4.2 million deaths worldwide. And approximately 91% of the people living in cities were exposed to particulate matter that exceeds air quality guidelines. Air pollutants can travel a long distance in as little as 4 to 6 days. In short, airborne particulates can affect a large number of people quickly. In the example we're going to show today, we're going to examine emergency releases. An emergency release is a kind of air dispersion model that deals with accidental releases. This kind of modeling is used to evaluate accident scenarios and to create emergency response plans. All right, so let's take a look at this application. What we have here is we have our sensor data, and we have 3 sensors. It's giving you information about those sensors. We have the sensors in the field themselves, and then we have information about the detection that can happen at this point. Take a look here, and that guy, and you'll note this is real-time data. So what happens is when a detection is signed, you basically get an update to that information. Now, in this particular case, we could actually automatically click off the dispersion model and have it go, but in this case, we decided to do it manually. And what it's doing is it's actually using the wind direction to predict the paths and pollutants through the environment. And ultimately, it's going to create the results of the contaminants on the ground themselves. So here we can see that it's after, I think this one was about 15 hours of data. And we can start to take a look at this data that comes back, keeping in mind that this is all about information on the ground or concentrations on the ground. So we're not really taking super advantage of the 3D side of it, but we'll get into that a little bit later. But it does give you a concept of how you can use this type of application to be able to predict where the actual dispersion is going to happen, and then use it as a mechanism to be able to plan your response. What we also wanted to show you is how you can integrate this type of modeling into a 3D environment. So what we have here is we've broken it up into a couple of components. We have a 3D map over here. We have a 2D map and a number of widgets that have been placed. So let's get this started. So this one here is over a 3-day span, and it's over Denver. And you'll notice we have a mesh model as well for Denver. As you zoom out, you get an idea of where the dispersion model is going to happen over these 3-day spans. Like before, we can look at concentration, but in this particular case, I'm looking at concentration as a line chart, not as a bar chart. You can do it however you want. There's all different ways you can actually do this. But you'll notice again how responsive this is. You can also pick a time slice and have that time slice change over time. And you can see how the actual dispersion model is moving around as the prevailing winds are affecting it. A very nice representation of that data. But what we really haven't done to date is we really have not got to a point where we can look at this in 3D. So now we're in 3D, and you can see the plume model, and you can start to filter on that plume model. We could have had the ground concentrations here as well, but in this case, we just wanted to show and demonstrate the 3D component of this particular aspect of the model. So if you take a look at this, I wanted to maybe concentrate and take a look at what's going to happen close within Denver itself. So to do that, what we can do is do a spatial intersection and have that spatial intersection limit where the plume is going to be shown. And once you've done that, again, just like before, you can start to look at how this is going to unfold, in this particular case, very close to the Denver area. Now, what I also wanted to show here was the performance, because you'll notice I'm actually zooming and passing around as this particular scenario is unfolding. So that's very nice to be able to do that kind of manipulation of the application itself. We also wanted to show how you could tie this type of modeling into demographics. So we have a plume model. This one is for 20 hours a day. And what it does is it can be used to show, you'll notice down here in the right-hand corner, it's looking at population at risk. And you can take a look, at total there's 700,016 population at risk. But you can, of course, blush through the data and move through the data and dynamically get an understanding of that population at risk. So that gives you a bit of insight into integrating a model into our application and then using that dynamically within the application itself. I'm cognizant of my time here. I'm going a lot quicker than what I would normally go, so I'm going to try and get us in under the 30-minute mark. So finally, let's move on to our fourth application, automated agriculture mapping and analysis. This application uses imagery to automatically identify which farms in Austria are eligible for EU subsidies. This example relies again on our geoprocessing and the data, because that's all critical to all of these applications. But more importantly, we actually decided to use machine learning as part of the geoprocess. So the machine learning we used here belongs to Hexagon Geospatial and is part of M.App Enterprise. The machine learning that we were using before was actually part of Lakes Environmental. But this application also uses the mobile components. One of the things we didn't do is we were really looking at the monitoring side of things. In this particular case, we also wanted to look at the actionable items. So with that in mind, let's set the stage. Austria has a farming sector characterized by small farms where farming conditions is difficult. Most of the farms are located in mountainous areas, and as a result, certain farmers can receive subsidies. To provide some perspective on the scale of this initiative, the surface area of Austria is 83,879 square kilometers, of which 2.57 million hectares is eligible farmland. And the AMA is responsible for distributing about $1.5 billion to 120,000 farmers in Austria. Unfortunately, issues of improper assessment and payments have occurred. Specifically, farms that were too rocky, too steep, or too tree covered received payments. A fair and equitable solution was needed, one that could automatically determine which plots of land could actually be farmed and hence which could receive payments. So to do that, we actually started off with an unprocessed satellite image for the entire country of Austria. And we had a geoprocess, and that geoprocess was to take that raw data and essentially create a thematic representation out of it. And that thematic representation was all targeted at different types of vegetation. But most notably, it was done to define which is not eligible for subsidies. Okay, so with that in mind, at first glance, you're seeing the spatial model for the first time. So this is a spatial modeling environment that allows you to build these spatial models. And at first glance, this looks like a pretty simple model. It basically has a collection of inputs. It has the radiometric and topographic correction component. It has the raster and vector processing component, or pre-processing component. And ultimately, it has rules and machine learning. And what you'll notice is the ellipse down here. And that ellipse means that it's a spatial model within a spatial model. So we can click on that spatial model and get information about the one that drives that. In this case, there's some optimization of classes, and there are some classification rules. We can click on that one, and we can get to yet another level of this particular spatial model. And here we can see that, yeah, this can get pretty complex because there's a lot of things going on here. But the beautiful environment of being able to drag and drop and test as you go makes this completely possible for people that are novice to the system. Excellent. So with this in mind, let's take a look and get back to where we started from. So now that we actually have that information was then tied to the plots of land that are spread throughout Austria. In this case, it's the farming plots of land. And you'll notice that we use two map views here. We could have done this in a single map view if we wanted to, but we just wanted to show how you can use configuration to change the look and feel of an application very easily. So what you'll notice is on the right, we have everything about eligibility, and on the left, we have everything about land use. And I know this is a German up here, but in essence, the key one is this last one, which is not eligible for subsidies. So let's continue on and just take a look at how this application can be used. So you'll notice that we tied the two windows together, and that allows you to basically move in and take a look at one of these plots of land. And simply by clicking on it, we determine that it's 98.68% eligible for subsidies. And then when we click on it over here, it gives you the breakdown of what that is. So you'll notice just up in here, there's a little bit that's not eligible. and then there's a component that's got sort of the low vegetation index and a medium vegetation index. So that gives you a good example of being able to quickly quantify what is available for subsidies. And this one, it makes total sense that this one would be a good one for subsidies. Remember that this was all automatically processed using our geospatial processing engine. If we go over here and take a look at another one, what you're going to notice is most of this plot of land is actually got trees on it. So when you click on it, you get a 37.57% eligibility. And then when you go over here, you'll notice that, yeah, 57% of it is actually ineligible. So that's just really nice to be able to do that type of interaction to kind of look at your data and also use this as a mechanism to talk with the public. Because remember, this is all about the funds that are being distributed. But what we really wanted to do is we also wanted to show some of the 3D capabilities and bring this into a 3D environment. So you'll notice we have a map window. We're currently looking down on that map window. And when we take a look at it and tilt it on its side, we can see a lot of plots of land, which are sort of this light green. And that makes perfect sense because they're up in the mountains and they're in these high slope areas. So if we move in specifically from slope to 40 to 60%, we get a concept that, yeah, they are there, and 79.4% of those are ineligible. And we can then, of course, turn on the slope just to kind of verify what we have makes sense. Excellent. Like any completely automated process, there's going to be outliers and hence potential for disputes. So this is actually where the mobile component comes into play. Namely, this mobile component can be used to respond to disputes and perform field checks. So what you have here is the actual mobile app itself. You can log into that mobile app and it automatically places you right into the where you're supposed to be based upon the GPS. So there's a plot of land that's here in this particular case. And what you can do is you can take a look at that plot of land with the farmer and you can actually make observations about that plot of land to basically update the database and therefore update the information associated with that plot of land. So that's a real nice feedback loop that allows you to basically take that information and get it collated. So a fantastic application for Austria. In closing, M.App Enterprise is a unified geospatial enterprise platform that allows companies to easily create, deploy, and manage domain-specific solutions. It is a single platform that can be used to easily connect to a wide array of data sources, effortlessly transform data into actionable information using a robust collection of geospatial processing approaches, and finally, intuitively create and deploy a wide array of collaborative geospatial applications that solve real-world problems. This concludes our presentation. Thank you again for taking time to be with us today. I hope you found the presentation interesting, and take care.
Thank you, Robert. What fantastic tools you brought with you today. Folks, remember to keep an eye on your inbox. We will archive the recording for today and have attendance certificates available for you, all of that landing in your inbox. We appreciate your opinions on the survey that on your way out. And thank you again to Robert for sharing his expertise and to Nile for her webinar support as well. Have a great day. Tell a friend about Hexagon Geospatial and Directions Magazine. We'll see you soon. Thanks.